Welcome back to this tutorial. We can discuss two more questions regarding the same topic, floating point number representation. The first question is, what is the decimal value of the floating point number C1T00000? Means the number is represented in hexadecimal notation. And here the number is represented in 32-bit single precision floating point IEEE format. Okay, so this is the hexadecimal representation of that particular single precision 32-bit IEEE representation. We need to get the decimal equivalent of the corresponding number. Okay, and the options are given like 28 minus 15 minus 26 and minus 28. So actually what we want to do here, in order to get the decimal equivalent, we need to perform the reverse operation. So the number is given here like this, and its binary representation is this. That means this single zero is represented using 4-bit binary equivalent. This is actually the hexadecimal notation. So each symbol in the hexadecimal form is converted or represented using 4-bit binary equivalent here. And this is the general syntax of our single precision IEEE format. First, the MSB bit. The single MSB bit is the sign bit. Next 8-bit form the bias exponent field, and remaining 23-bit form the mantissa field. Okay. So based on this binary pattern, here it is. The sign bit, the MSB single bit, the sign bit is 1. Means the given number is negative. If it is 0, then we can conclude the given number is positive. Here it is negative because of this MSB value 1. Now we need to consider the next 8 bit. This next 8 bits form the bias exponent field. So the next 8 bit is 100000011. Okay, its decimal equivalent is 131. Okay, so this is actually our bias exponent. This is the single precision representation, and the bias value is 127. So this is the decimal equivalent of our biased exponent. To get the actual exponent, what we want to do, simply subtract the bias value 127 from this biased exponent value. That is 131 minus 127. We get the actual exponent as 4. Okay. Now we can consider the remaining, that is the mantissa field. Here the remaining values like this, 101 and all zeros. Okay, so this is the mantissa field, but we need to concentrate on one point over here. That is, in the normalized form, we have a default 1 over here. That is, the normalized form is actually 1 point something. So, after discarding this 1 before this fraction point, the remaining part is taken as the mantissa. Right. So, we need to consider that default 1 while converting into its decimal equivalent. Okay. So, the actual number here is, sign is negative, that is why minus, and the default 1. Okay, in the normalized form, we have one default 1 before the decimal point. So, minus 1 point, then the mantissa field value like this into 2 to the power actual exponent. Okay, now we can distribute this exponent over here and we get minus 11010.000. Okay, we can shift this decimal point 4 position towards right. That is equivalent to this into 2 to the power 4. Okay, so after this exponent distribution, we have the representation like this. The fractional part is completely 0 now. Now, this 0 is at 1's position. That is 2 to the power 0 into 0 plus 2 to the power 1 into 1. That is 2. Plus, here again 0. And next we have 1. That is 2 to the power 3 into 1. That is 8. Plus 2 to the power 4 into 1. That is 16. And the number is negative. So while adding, we get negative 26. So option C is the right answer. So in this type of questions, that is the conversion from the IEEE single precision representation back into its decimal equivalent, you must include that default 1 before this decimal point. The second question is, the value of a floating type variable is represented using the single precision 32-bit floating point format IEEE 754 standard that uses 1 bit for sign, 8 bit for biased exponent and 23 bits for mantissa. That is actually the description about our single precision format. A float type variable x is assigned the decimal value of minus 14.25. A decimal fractional number is given here. Its corresponding hexadecimal notation based on single precision format is needed. A decimal value for minus 14.25 is given. Its hexadecimal representation of single precision notation is required. So options are given like these. Okay. So consider that general syntax of our single precision representation: single bit sign, biased exponent, 8-bit field, mantissa, 23-bit field. The given number is minus 14.25. Okay. So we need to convert this into its binary equivalent first. The sign bit is, it's clear that the sign is negative, so sign bit must be 1. Next, the binary equivalent of 14. Binary equivalent of 14 is 1110. Next, we need the binary of 0.25. So, the binary of 0.25 is 0.01. Okay. So, minus 14.25 is equivalent to this 1110.01 in binary. So, our next step is normalization. The normalized form is 1 point mantissa into 2 to the power exponent. Okay. So, in order to make this in the form of 1 point mantissa, we need to shift this decimal point 3 position to the left like this. 1.11001 into 2 to the power 3. So from this normalized form, the actual exponent is 3. But here we needed the biased exponent. So we need to add the bias value 127 with this actual exponent and get 130 as the biased exponent. Its binary equivalent is this. Okay. Next is about the mantissa, and this is the mantissa part. 11001. So, sign bit is 1. The biased exponent is 10000010 in 8-bit representation and mantissa in 23-bit representation. 11001 and all other bits are 0 in the mantissa field. Okay, so here we need the hexadecimal equivalent, hexadecimal representation for the single precision representation. So we can group these values from right towards left, and each group contain 4 bits. So here it is hexadecimal 0, 0, 0, 0, 4, 6, 1, C. Like this. This means 0. These three groups again zeros, and this is hexadecimal 4, and this 0, 1, 1, 0. That is hexadecimal 6, 0, 0, 0, 1, hexadecimal 1, 1, 1, 0, 0 is C in hexadecimal. So option A is the right answer. Okay, thank you.